This is video 7D for the Year 11 Mathematical Methods course. In this video we're going to be covering some example questions from the tangent function, under the topic of trigonometric functions. The 8 questions we will be going through are now displayed on the screen, so I recommend that you attempt these questions before watching the rest of this video. Question 1. What is the period of y equals tan of 3x take pi? So the tan function that we're working with here is y equals tan of 3x minus pi. Now the first thing that we need to do here is rewrite this bracket in the standard form for a tangent function. And to do that we need to factorize this 3. So by factorizing this 3, we get y is equal to tan of 3 multiplied by x take pi over 3. And so we now know that the period of a tan function is given by pi divided by this value here. So in other words, the period is equal to pi divided by 3. Question 2. Describe the transformations that map the graph of y equals tan of x to the graph of y equals tan of 4x. So we have the function of y equals tan of 4x, and in this case we only have one transformation that we need to be concerned about, and that is the transformation caused by this 4. And so we know in this case that this transformation is going to be a horizontal dilation by a factor of 1 over 4. And so therefore the period of the graph is going to be pi over 4. So if we want to describe the transformations that map the graph of y equals tan x to the graph of this function here, we can just say that the graph of y equals tan of x is dilated horizontally by factor 1 over 4, and that the graph has a period of pi over 4. Question 3. Describe the transformations that map the graph of y equals tan of x to the graph of y equals tan of 2x minus pi. So we have the function of y equals tan of 2x minus pi. Now before we do anything here, the first thing that we need to do is rewrite this bracket in the standard form for a tangent function. And in order to do that, we're going to factorize this 2. So by doing this factorization, we get y is equal to tan of 2 multiplied by x take pi over 2. And so what we can do now is identify our b and c values. So b in this case is 2, and c is going to be pi over 2. And so now if we want to describe the transformations that map the graph of y equals tan of x to the graph of this function here, we can say the following. First things first, because b is equal to 2, this means that we're going to have a horizontal dilation by factor 1 over 2, and therefore the new period of the graph is going to be pi over 2. And secondly, since c is equal to pi over 2, then this means that the graph is going to be translated to the right by pi over 2 units. So, in summary, the graph of y equals tan of x is dilated in the horizontal direction by a factor of 1 over 2, and so therefore the graph's period is now pi over 2, and it is also translated to the right by pi over 2 units. Question 4. Sketch the graph of a tangent function of y equals tan of 2x on the domain of x being between 0 and 2 pi. So the tangent function that we have here is y is equal to tan of 2x. Now let's insert a set of axes that we can sketch the graph on. And so for this particular set of axes, we're going to say that every 4 grid lines along the x-axis represents pi. So in other words, this point here is pi, and this point here is 2 pi. And now the first thing that we're going to do is plot out all the important points for the basic tangent function of y equals tan of x. So for y equals tan of x, we know that we have an x-intercept at x equals 0, x equals pi, and at x equals 2 pi. And furthermore, we know that we have vertical asymptotes at x equals pi over 2 and x equals 3 pi over 2. So these vertical asymptotes I'm going to represent using hollow circles. Now, the only transformation that we need to consider in this case is the fact that we now have a 2 as the coefficient of x. And what this coefficient is going to do is it's going to dilate the graph in the horizontal direction by a factor of 1 over 2. So in other words, we're going to get all the x coordinates of these points and we're going to half them. So this point here isn't going to move anywhere. This point here gets shifted down to pi over 4. This point here gets shifted down to pi over 2. This point here gets shifted down to 3 pi over 4. And this point here gets shifted down to pi. So now we know that the graph is going to cut the x-axis at this point here, and this point here. And we're going to have vertical asymptotes at this point here and this point here. So first of all, let's draw some dotted lines to represent these vertical asymptotes. And so now by sketching the graph, we get the following. Now the only problem here is that because we dilated all these points by a factor of 1 over 2, we now also need to consider what this graph is going to look like between pi and 2 pi. Luckily for us, we can see a very nice pattern that's going on here. In that, every time we move over to the right by pi over 4 units, we alternate between an x-intercept and a vertical asymptote. X-intercept, vertical asymptote, x-intercept, so then we can continue that pattern in the right-hand direction. And so we therefore know that we're going to have another vertical asymptote here, an x-intercept here, a vertical asymptote here, and an x-intercept here. And so now by sketching out the rest of this function, we get the following. Question 5. Sketch the graph of the tangent function y equals tan of x take pi over 2 on the domain of x being between negative pi and positive pi. So the tangent function that we're working with here is y equals tan of x take pi over 2. So now we're going to insert a set of axes that we can sketch this graph on. Now for this particular set of axes, we're going to say that every 8 grid lines on the x-axis represents pi units. So this here will be at negative pi, and this here will be positive pi. Now, first thing that we're going to do here is plot out all the important points of the basic tan function of y equals tan of x. So for y equals tan of x, we have an x-intercept at negative pi, 0, and at positive pi. And we have vertical asymptotes at x equals negative pi over 2 and positive pi over 2. For now, we're going to represent all the vertical asymptotes with a hollow circle. Now, the only transformation that we need to take into account here is this minus pi over 2. Which will translate the graph to the right by pi over 2 units. So in other words, we're now going to translate all these important points to the right by pi over 2 units. So this point here is going to get shifted to negative pi over 2. This point here is going to get shifted to 0. This point here is going to get shifted to pi over 2. And this point here will get shifted to pi. So now we have x-intercepts at negative pi over 2 and positive pi over 2. And we also have vertical asymptotes at x equals 0 and at x equals pi. So let's draw out some vertical dotted lines to represent these asymptotes. And so we can now sketch out the following parts of the graph. Now this is all well and good, the only problem now is that we don't have a section to draw for this last part here. However, what we can realize is the fact that this particular graph follows a very nice pattern. In that, every time we move to the left or right by pi over 2 units, we alternate between an x-intercept and a vertical asymptote. Which means that because we have an x-intercept here, it means that we're going to have a vertical asymptote at x equals negative pi. So let's just represent that here and draw the vertical dotted line. And so now we can extend this graph into the following. Question 6. Write the equations of all vertical asymptotes of the graph y equals tan of b multiplied by x minus c in terms of b and c. So here we're considering the general tan function of y equals tan of b multiplied by x takes c. Now the way that we're going to have to tackle this question is by starting off with the equations of all the vertical asymptotes for the basic tan function. Because we can recall that for y equals tan of x, then the equation for all vertical asymptotes is x equals pi over 2 plus k pi, where k is just some integer. Now the reason why this is important is because now we're going to have to apply the transformations of B and C on this equation for the vertical asymptotes to then write the equation for all the transformed vertical asymptotes. Now, the key thing to keep in mind with this equation here is the way that we essentially form this is we start off with the position of the first positive vertical asymptote, and then we add a multiple amount of the period. And so all we need to do here is consider how these values of B and C affect the position of the first positive vertical asymptote, and also how they affect the period of the graph. Now, if we consider what these values of B and C do, we of course know that B induces a horizontal dilation by factor 1 over B, and then C induces a horizontal translation to the right by C units. And so what we're going to do now is consider how both of these transformations here affect the position of the first vertical asymptote and how they affect the period. So let's first of all look at how the horizontal dilation affects both of these things. Now we want to apply these transformations in order from left to right, so let's first of all consider how the horizontal dilation affects these two things. So the original position for the first positive vertical asymptote is at pi over 2. However, because we're now dilating this by a factor of 1 over b, we now need to multiply this by 1 over b, which gives us an answer of pi over 2b. And furthermore, with the period, because we originally have a period of pi, then we need to dilate this by a factor of 1 over b, which gives us a new period of pi over b. Now, moving on to the second transformation, let's consider how the translation affects these two things. So, after the horizontal dilation, we know that the position of the first vertical asymptote is going to occur at pi over 2b. So now if we shift this position to the right by c units, then we know that the first positive vertical asymptote will occur at this point plus c. And then secondly, we know that translations do not affect the period of the graph at all, so therefore the period of this graph is still just this pi over b. And so now we have the transformed position for our first positive vertical asymptote, and we have the new period for this particular function. So therefore, combining these two, we can say that the equations for all of the vertical asymptotes for this particular function is going to be x equals the position of the first positive vertical asymptote, which is pi over 2b plus c, plus a multiple amount, so k lots of the period, which we've just found to be pi over b. So in other words, the equations for all the vertical asymptotes are now x equals pi over 2b plus c plus k pi over b, where k is just an integer. Question 7. Find the equation of a tangent function with the following graph. Alrighty, so in a question like this, our ultimate goal is to write the tangent function in the following format. Y equals tan of b multiplied by x takes c. And our job is to find the values of b and c. So let's first of all bring back the graph that we had in the original question, just so we can analyze it a little bit further. Now, first things first, we know that in order to calculate b, we get pi, and then we divide it by the period of the graph. And in order to find the period of this graph, we're going to use these two vertical asymptotes. We notice that the first vertical asymptote is situated at x equals negative pi over 4, and that the second one is situated at x equals 3 pi over 4. And so then the horizontal distance between these two is pi units. So this means that b is equal to pi divided by pi, which is equal to 1. Now, in order to calculate the value of c, we're going to consider the position of this first x-intercept here, which is positioned at x equals pi over 4. Because we know that for the basic tan function of y equals tan of x, then the first x-intercept occurs when x is equal to 0. And because the value of b is equal to 1, we don't need to consider any horizontal dilation for this part here. And so therefore, because on this graph over here, the first x-intercept occurs at x equals pi over 4, this means that we've got a translation to the right by pi over 4 units. Which therefore tells us that c is equal to pi over 4. So we found that c is equal to pi over 4, b is equal to 1, so now let's substitute both of these back into the general tan function. So we have y is equal to tan of x take pi over 4. Now, in order to double check this answer, we're going to come over to our graphics calculator, plot out the graph of this function here, and confirm that it matches the original graph that we were given. So we will also set the same viewing window as in the original graph. So we're going to set the minimum x value to be negative pi, and the maximum x value to be 3 pi over 2. Now, first things first, let's confirm that the x-intercepts match up. So on the original graph, we have x-intercepts at negative 3 pi over 4, positive pi over 4, and positive 5 pi over 4. So let's confirm that we get the exact same thing with our function. So at negative 3 pi over 4, we have an x-intercept, which is great. At positive pi over 4, we have another x-intercept, which is really good. And then finally, at positive 5 pi over 4, we have another x-intercept. So this is all good to go here. Now let's quickly confirm that we have vertical asymptotes at x equals negative pi over 4 and at x equals positive 3 pi over 4. So at x equals negative pi over 4, we have an error, which means that we've got a vertical asymptote, which is really good. And at positive 3 pi over 4, we have another error, which means that we've got a vertical asymptote there. So all the key components line up with one another, which therefore means that what we've got here is correct. Question 8. Find the equation of a tangent function with the following graph. Alrighty, so with this type of question here, we want to try and write our tangent function in the following format. Y equals tan of b multiplied by x takes c. And our goal is to find the values of b and c. So let's quickly bring back the original graph from a question just so we can analyze it a bit further. Alrighty, so first things first, we know that b is equal to pi divided by the period of the graph. And in order to find this period, we're going to use these two adjacent vertical asymptotes here and here. Because the first vertical asymptote is situated at x equals negative pi over 4, and then the second one is situated at x equals positive pi over 4. So what that therefore tells us is that the horizontal distance between these two vertical asymptotes is pi over 2 units. And so this means that b is equal to pi divided by pi over 2, which is equal to 2. Now, in order to find the value of c, we're going to use the fact that our first positive vertical asymptote occurs at x equals pi over 4. Because we know that for the basic tan function of y equals tan of x, that the first positive vertical asymptote occurs at x equals pi over 2. However, we also need to take into account the fact that this graph is being horizontally dilated by a factor of 1 over 2. And so therefore, after this horizontal dilation, this first positive asymptote should occur at x equals pi over 2 divided by this 2, which is equal to pi over 4. So in other words, after this horizontal dilation, our first positive asymptote should occur at x equals pi over 4, and we notice that with our graph, our first positive vertical asymptote indeed occurs at x equals pi over 4. And so what that therefore tells us is that there has been no horizontal translation. Which therefore tells us that c is equal to 0. And so we found that c is equal to 0, b is equal to 2, so let's substitute both these values into the general tan function. And now, in order to double check this answer, we're going to come over to our graphics calculator, pop in the function that we have, and confirm that we get the exact same graph as what we started with at the start of the question. And so the first thing that we're going to confirm here is that we have x-intercepts at x equals negative pi over 2, 0, and positive pi over 2. So if we first of all look at the graph when x is equal to negative pi over 2, then we have an x-intercept. When x is equal to 0, we have another x-intercept, and when x is equal to positive pi over 2, then we have another x-intercept. So these here are all good so far. Then the second thing that we want to check is that we have vertical asymptotes at x equals negative pi over 4 and at x equals positive pi over 4. So if we first of all check out when x is equal to negative pi over 4, we have an error, which therefore tells us that we have a vertical asymptote at this point. And similarly, if we check out positive pi over 4, then we again have an error, which again tells us that we have another vertical asymptote, which is exactly what we want. So all the key features are matched up with our answer, which is really, really good, because now we can be confident that the answer that we have is indeed correct.